Hello everybody, this is Dr. Christopher White, and in this presentation we're going to begin thinking about geologic time. So when dealing with geologic time, the first thing a geologist has to be able to do is we have to be able to date a layer or sequence of rocks. So how are geologists going to go about doing that? Well, geologists can use one of two possible techniques to date a layer of rock or a sequence of rocks. The first technique is referred to as relative dating, the second technique is referred to as absolute dating. Now, in the case of relative dating, what you're doing is you're putting a sequence of rocks into a chronological order. So let's say you walk up to a cliff face. You're going to look at that cliff face and maybe you will see a dozen or 24 different rock types. What you're going to do is you are then going to try and put those rock types into a chronological order. So you're going to say, right, this layer formed first, followed by this layer, followed by this layer, followed by this layer. So what you're doing essentially is you're putting the layers into a chronological sequence. So you're producing a story, an ordered story of how that particular cliff face formed over time. Now, the thing that you will have instantly spotted is that what we've done is we've produced a relative sequence, so the rocks are dated relative to each other, but there's no numerical values associated with those layers of rock. So it's not like we can use relative dating to say, right, this layer of rock was 400 million years old, this layer of rock is 250 million years old. We can't do that. Now, the other technique is called absolute age dating, and this is also sometimes referred to as numerical or radiometric age dating. And this particular technique uses radioactive decay. So there are some minerals which will contain very small quantities of radioactive isotopes, of which, arguably the most commonly known would be something like uranium. Now, as long as we know how much uranium was in the mineral when it formed, and how quickly that uranium decays, we can essentially use the uranium like a clock to date that particular crystal. And of course, the assumption then is that the formation of that crystal occurred at the same time as the actual rock itself formed, and so you can use those crystals to date the rocks. Now, you have to remember that absolute age dating wasn't actually available to geologists until the 1940s at earliest, and didn't really become particularly widespread until the 1970s and 1980s. So this means that the vast majority of dating which was done by geologists is actually what we refer to as relative dating. So we've tried to put all the layers of rock into a sequence. It wasn't until later on that we could actually come in and start putting numerical values to certain layers of rock. Now, there's a couple of problems when it comes to absolute age dating. The first problem is that you can only really use it to date certain rock types. Igneous rocks are very often the easiest rocks to date using absolute age dating because they commonly have the types of minerals which we can use. You can also use absolute age dating to date metamorphic rocks, although the process of metamorphism can often have an effect on the minerals you're trying to date, and so you can very often get incorrect values. In terms of sedimentary rocks, it's actually quite tricky to produce absolute age dates for sedimentary rocks, typically because the types of minerals you want to use aren't present, or if they are present, they weren't actually formed as part of the sedimentary rock. So let's think of a situation where you are weathering a granite. So in the process of weathering that granite, you're obviously going to produce lots of clasts, and those clasts are going to contain some of these minerals which we can use for dating. The thing is that the clast becomes incorporated into a sedimentary rock. So if we try and date that sedimentary rock, what we're doing is we're dating the age of the clast, which will give us the age of the granite, not the age of the sedimentary rock itself. So you can see how there's a bit of a problem. The other problem with absolute age dating is that it's actually pretty expensive. It's a very tricky process. You're dealing with very small quantities of radioactive elements, typically in crystals, which are themselves very, very small. So you need very, very accurate measurements. So you have to have, the best quality scientific equipment out there. And of course, this is going to come with an associated price tag. So typically, the vast majority of dating that geologists do is relative dating. And so we'll do this on a local scale for a cliff face, we'll do it on a county scale, we may do it on a state scale, we may do it on a countrywide scale, and the plan will be to try and produce a complete stratigraphic sequence for an area, going from the earliest rocks you can find all the way through to the youngest rocks you can find. And this might require you to go to multiple different locations to actually produce this stratigraphic column. So the first thing we're going to think about is how do we infer the age of a layer of rock using relative dating? And this is going to correspond to section 9.1 of your textbook. So if we have a look at these two images here, what can we see? Well, to begin with, we can both see that they can see straight away that these images are both images of a sequence of layers of rock, most likely sedimentary. So you can see in this case we have relatively nice horizontal layers, whereas in this case we can see the layers quite clearly have dip to them. They've been tilted. Now, in geology, what we assume is that most sediments will initially be deposited as horizontal sheets. So when you look at a layer of sedimentary rock, you can say with a relative degree of certainty that that layer of sedimentary rock would have started its life as a horizontal sheet of sediment that was then lithified to produce a sedimentary rock. Now, this means, therefore, that when we see a sequence of rocks which have been tilted, this does not represent the original situation. So originally our sequence of rocks would have looked something like this, but when we look at this sequence of rocks here, we can quite clearly see that they've been deformed in some way. And so this quite clearly tells us that this deformation must have come after the sediment was lithified to give us a sedimentary rock. So our sediment was deposited, it formed a sheet, that sheet was lithified to give us a sedimentary rock, and then that sequence of sedimentary rocks was deformed to produce the dip that we can see here. So this is referred to as the principle of original horizontality. And as you can see, it's giving us a method of timing when deformation occurs. So we know that any deformation that occurs to this sequence of rocks here must have occurred after the rock formed. So you can see straight away we have managed to relatively date deformation when compared to our sequence of rocks here. So we can see in this sequence we have several different layers of rocks, all showing different colours. You will notice that all of these different layers of rocks have been deformed. And so this means that this complete sequence of rocks here must have formed and been lithified to produce sedimentary rocks, and then the sequence must have been deformed. And so this tells us that this deformation must have occurred after the youngest layer of rock in the sequence. So the next thing we're going to think about is how layers of sediment are deposited. So if we look at this situation here, you can see we have this grey layer of rock here, which is often referred to in geology as the basement. So the basement is the material on which new layers of sediment are going to be deposited, and we can see that in this particular situation we have this tan-coloured layer of sediment being deposited, and we're not going to worry about what type of environment it's being deposited in. It's just being deposited, and we've ended up with a nice sheet of sediment which obviously is going to get lithified to give us a sedimentary rock. Now, over time, what's going to happen is the conditions are going to change slightly, and we're going to get a new layer of sediment being deposited. This new layer of sediment is red in colour, and you can quite clearly see it's being deposited over the top of the tan layer. Then we're going to have a third layer of sediment being deposited, and this one is going to come over the top of the red layer here. So you can see now we have a sequence of 4 different layers of rock. And so we need to think, right, when we look at this sequence, which layer of rock is going to be the oldest and which layer of rock is going to be the youngest? Well, this one's relatively easy. So in this sequence, it's obviously going to be the layer of rock at the bottom, which is going to be the oldest, and the layer of rock at the top, which is going to be the youngest. And in geology, this is referred to as the principle of superposition. And it states that the layer of rock at the bottom of the sequence will typically be the oldest, and the layer of rock at the top of the sequence will typically be the youngest. And this will work in the vast majority of cases. So, in 97–98% of cases, when you see a sequence of rocks like this, you can say, right, the oldest layer is going to be at the bottom and the youngest layer is going to be at the top. There are a few examples where this would not work. So there are situations where the sequence of rocks have been overturned, so the sequence has actually been flipped around. So the rock which is actually the oldest has been taken to the top of the sequence, and the rock which is the youngest has been pushed to the bottom of the sequence. But geologically speaking, that's much rarer. So we don't often see sequences which have been overturned. And so this means in the vast majority of cases, superposition shows us that the sequence of rocks is getting younger, in an upward direction. So once again, superposition, oldest layer of rock at the bottom, youngest layer of rock at the top. So if we look at this picture here, you can see that we have a picture of the Grand Canyon. So what can we see when we look at this particular image? Well, obviously we know from the principle of superposition that this sequence of sedimentary rocks that we can see here is more than likely going to have the oldest layer at the bottom of the visible sequence, and that means right down here in the river valley. So this is where the oldest rock in the sequence is going to be located. Obviously, based on superposition, therefore, the youngest layer of rock is going to be the layer of rock at the top of the sequence coming across here. And so we know as we move from the bottom of the sequence and come up toward the top of our sequence, the rocks are progressively getting younger. Now, we can also see that this entire sequence of rocks has clearly been cut by the Colorado River, producing this river valley. And obviously within this river valley, we can see we have sediments that have been deposited. So once again, in geology, what can we say when we look at this? Well, first of all, as a geologist, we'll go, right, this layer is going to be the oldest, this layer is going to be the youngest, and so we know our sequence of rocks is getting younger as we go upwards. And we know that because of the principle of superposition. Now, if we look at this sequence here, we can see that our sedimentary layers are on the whole pretty horizontal. And so this would suggest that the sequence hasn't undergone any significant deformation. So we don't have to worry about that. What we can see, though, is that clearly after the youngest layer of rock was deposited, there's clearly been substantial erosion. And obviously this erosion is due to the presence of this river. And so, over time, this river has cut down through the sequence of rocks, and it's produced this river valley that we can see right here. And so this means that we know straight away that the erosion and the sediments produced by that erosion within the river valley must therefore be younger than the youngest layer of rock in our sequence here. And so once again, we're coming up with a chronological order of events which are occurring in this area. Now, if we look at this sequence here, we can see that our layers of rock have quite clearly been tilted. Now, what we're going to try and do is we've got to try and work out, right, well, which one's going to be the oldest and which one's going to be the youngest. And actually, this can be surprisingly tricky. So if we look at this picture here, would it be a situation of this would be the youngest rock here, the oldest rock here, and it's getting younger this way? Or could it be a situation where the sequence has been overturned and the oldest layer of rock would be here and the youngest layer of rock would be over here? So when we're dealing with sedimentary rocks that have been deformed, we always have to be pretty careful because we don't want to get our superposition in the wrong order. Now, as per usual, the upper layers will obviously be the youngest and the lower layers will typically be the oldest. So when we look at this sequence, we can assume that these upper layers up here are probably going to be the youngest, and these layers over here towards the bottom of the sequence are more than likely going to be the oldest. And so that would suggest that it's younging upwards like so. But we have to be very, very careful when thinking about deformation, and we have to know exactly how the rocks have been deformed before we can be certain that we've got our sequence in the right direction. Now, obviously, once again, you can see we have a sequence of sedimentary rocks here. And so assuming that superposition is going from oldest rocks over here to youngest rocks here, that would obviously mean that we have our layers of sediment being deposited, those layers of sediment get lithified, and we know from the principle of original horizontality that those sedimentary rocks which are produced are going to be horizontal in orientation. Now, this therefore means the tilting that we can see here must therefore have occurred after all of these rocks were deposited and lithified. And so we know the deformation occurs, and then we can quite clearly see once again, we have ourselves a river here which has clearly eroded down through the sequence. So we know we have this layer of sediment was deposited going through the sequence up to this layer of sediment. The entire sequence was then lithified, it was then deformed, which tilted it, and then there was erosion, which was the result of this river passing through the area. So you can see, once again, we're building up this chronological sequence of events. So what's the next method of relative dating that we can use? Well, if we look at these pictures here, we can see we have a situation where we have pieces of rock contained within other rocks. Now, depending on what type of rock you're dealing with, these pieces of rock will be given different terms. So in the case of a sedimentary rock, these chunks here would be referred to as clasts. In the case of an igneous rock, you're dealing with something which we refer to as a xenolith. So in this particular instance here, we can see that we have a granite, which is this darkish grey, well, medium grey rock here. And you can see within this granite, we have pieces of this dark grey to black rock here, which we can see is more than likely metamorphic. And we know this because if we look at this picture right here, you can actually pick out the sweep of a fold right there. And so this means that this rock has clearly undergone some form of ductile deformation, and so we can say with a relative degree of certainty it's going to be a metamorphic rock. So we quite clearly have metamorphic rocks contained within a granite. Now, obviously, if we're going to have these pieces of metamorphic rock within our granite, how did they get there? Well, you have two possible options. Either the metamorphic rock was there first and pieces of it went into the magma, which eventually solidified to give us the granite, or somehow the granite was intruded and then the pieces of metamorphic rock somehow entered it. I think we can agree that the second option isn't really going to happen. It's very unlikely that kind of event could occur. So in this particular instance here, what we have is we have these excuse me, we have these xenoliths of metamorphic rock here, which have obviously fallen into the magma, and that magma has then cooled down over time to give us the granite. This means, therefore, that the xenoliths that we can see here must be older than the granite in which they are included. So in this case over here, you can see we have a layer of conglomerate. So if you remember, a conglomerate is a coarse-grained clastic sedimentary rock where the clasts are 2 millimeters in size or larger. So as we can see in this case, we have some extremely substantial clasts within our layer of conglomerate, and these clasts are made up mostly of basalt. Now, this obviously means that these clasts are going to be classified as clasts rather than xenoliths because we're dealing with a sedimentary rock. But once again, in order for these clasts of basalt to actually become incorporated into the conglomerate, the basalt must have been there first. There's no other way it can really happen. And so this means that the pieces of basalt that we can see here within the conglomerate must therefore be younger than the conglomerate itself. Must therefore be older than the conglomerate. I do apologise for that. So the basalt must be older than the conglomerate in which they are included. So this is referred to as the principle of inclusions, and it simply says that if you have an inclusion of a rock within another rock, the inclusion must be older than the rock in which it is contained. So now we're going to think about some other features that we tend to see in sequences of rocks. So if we look here, we can see we have a sequence of limestones, and you can see it's quite a nice or near horizontal stratified sequence. So straight away, principle of superposition says the oldest rock is going to be at the bottom and the youngest rock is going to be at the top. And that's a relatively safe bet because we can see this sequence appears to show no real noticeable deformation, and so we think it is quite likely that this sequence will not have been overturned. And so straight away, the principle of superposition says, right, oldest at the bottom, youngest at top. Also, when we look at it, we can see that these layers of rock are approximately horizontal, and so this would suggest there's been little to no deformation taking place. Now, when we look at this sequence of rocks, though, we can see there are some extremely large joints cutting across the bed, and we can see the joints are essentially top to bottom like so. So straight away, we are now going to try and work out a sequence of events. So here we have a situation where we know the oldest sediment was going to be down here, and then as more layers of sediment were deposited, we have these layers of sediment becoming lithified to give us rocks. And so we know the oldest rock is going to be at the bottom, the youngest rock is going to be at the top, and then we're going to look at the position of these joints. Well, we can see, especially when we look at this joint right here, it cuts through the entire sequence. So all of these layers must have been present before the joint formed, because if they weren't there, there's no way the joint could cut through them. And so we know straight away that this is the oldest layer of rock here, this is the youngest layer of rock here, and then we know after that entire sequence formed, then the joint formed. And so once again, we've gone and come up with a chronological order for what we can see in this cliff. Now, the same thing would happen if we had a fault here. So let's imagine this is a fault and this block of rock, let's say, has dropped down relative to this block of rock over here. Well, once again, we know before that fault forms, all of the rocks here must have been essentially solidified. They must have been there. Because once again, you can't cut something if it doesn't exist. And so we know that if this was a fault, therefore once again this entire sequence of rocks must have formed, then they had to be cut by the fault. So once again, we've managed to date when the faulting occurred. And so you can see straight away, when we have joints, when we have faults, they must be younger than the rocks which they cut, because the rocks have to have been there first before the joint or the fault could form. So the same thing goes for dikes. So if you remember, dikes are essentially the conduit through which magma moves in the subsurface. And so we can see in this particular instance here, we have the dikes, which are picked out by this rather tan-coloured rock right here. And you can see these dikes are moving through this darker coloured igneous rock. So obviously, in order for these dikes to have been in place, the igneous rock, the dark igneous rock, must have been there beforehand, mustn't it? Otherwise this process could not have occurred. And so straight away we know this dark igneous rock must therefore be older than the lighter rock here, which is clearly cutting through them. So this is referred to as the principle of cross-cutting relationships, and it simply states that joints, faults and dikes must be younger than the layers of rock through which they pass, because obviously they can't, there's no way they could cut through those layers of rock if the layers of rock weren't already there. The rock has to be there before you can, crack it to create a joint or a fault. The layers of rock have to have been there before you can intrude a magma into it to produce a dike. So the final feature we're looking at is, final feature we'll use for relative dating is due to the heat that comes from magma. So if we look right here, what we can see is we have a dike, and here's our dike here. It's this dark coloured rock right there. Now the dike, as we've said, must be younger than the rock which it is passing through. So we know that the dike here must be younger than the rock which it is intruding, which is this older grey rock right here. Now the thing you'll notice though is that at the contact between the dike and the country rock which it's intruding, you'll see there's a noticeable change in colour. We have a black dike here, we have this kind of greyish green rock here, but the contact between the two is picked out by this slightly rusty red kind of colour. Now this is referred to as a baked contact, and the formation of a baked contact is due to the heat from the magma heating up the rock which it's in contact with and causing the minerals to change. It's a form of contact metamorphism, and the mineralogical changes caused by this heating obviously produces a rock that has different physical properties to the original rock which is being heated up. And so that's why this baked contact here has a different appearance when compared to the original rock. We can also see the same thing occurring here. So this entire large sequence here, this kind of grey to tan coloured rock here, is a lava flow, and beneath it we have a sequence of other older rocks here which we can see have this kind of distinct rusty red colour to them. So straight away the principle of superposition says youngest layer at the top, oldest layer at the bottom. So we can assume that this layer here is going to be the oldest layer and this layer here is going to be the youngest layer. So we've managed to come up with a chronological order straight away. But we can give this extra we can be extra certain if we use the principle of what's referred to as the principle of baked contacts. So if we look at this picture situation here, here's our lava flow and it's moving across the surface of the earth. So this boundary right here used to be the surface of the earth. It used to be a surface on which you or I could have possibly walked. Now, what happened is at some point there was obviously a volcanic eruption, lava got extruded from the volcano, and this particular surface got covered over by this lava flow. Now, we know that lava flows by their very nature are hot. And so as the lava flow moved over the surface, what did it do? It started to heat up the rock which it was in contact with. And this heating up of the rock went and produced this dark red to black contact which we can see right here. So this is our baked contact which is being produced due to the heat of the lava flow. And so, although the principle of superposition says this is the oldest rock here and this is the youngest rock here, we can add extra detail and be extra certain by using the principle of baked contact. We can say, right, we can see the baked contact right here, and so we know that this layer of rock, which we can see in the bottom half, must have been heated up by the lava flow that passed over the top of it. Therefore, this layer of rock has to have been there beforehand, so it has to be the older layer, and this layer of the lava flow must therefore be younger. Now, this particular technique is actually very helpful when it comes to dealing with sills. So if you imagine you have a sequence of rocks, and you've got a sedimentary rock, another sedimentary rock, another sedimentary rock, and then you have a layer of igneous rock, and then you have some more sedimentary rocks above it. Now, in this particular sequence, when you look at it, the first thing you'll think to yourself is, right, well, I can see there's a layer of igneous rock right there. The question is that layer of igneous rock going to be a lava flow? Or is that layer of igneous rock going to be a sill? If you remember, a sill is like a dike, but it's intruded along the bedding plane between layers of rock. So we have two layers of rock, and the magma gets injected along the contact in between them. So it essentially produces a horizontal dike, which we refer to in geology as a sill. So the question becomes how do we work out whether our igneous rock is a lava flow or our igneous rock is a sill? So if we look at our sequence of rocks, so imagine there are several layers of sedimentary rock down here, and we're moving up through our sequence and we're coming towards our layer of igneous rock. And as we transition from our sedimentary rocks into our igneous rocks, we can see that there is a baked contact right here. Okay, so we know therefore that the magma must have heated up the rocks below. Now, as we continue up through our igneous rock, we then come to the top of our layer of igneous rock, and then we pass up into the sedimentary rocks above it. Now, if there is no baked contact along the top of our layer, we therefore know that the layer of igneous rock must have been a lava flow. We know this because as a lava flow moves across the surface of the Earth, it's obviously going to bake the rocks directly below it. But because it's a lava flow and it's moving across the surface of the Earth, there are going to be no rocks above it which it can bake. And so this means there's no baked contact along the top of lava flows when we look at our sequence of rocks. In contrast, if it was a sill which had been injected along a contact between two layers of rock, well, in that case, we're going to see a baked contact along the bottom, and we're going to see a baked contact along the top, because the layers of rock will already have been there, and then the sill was injected, and then the magma will have heated up the rocks at the bottom of the sill and at the top of the sill, creating two distinct baked contacts. All right, thank you for watching, everybody, and have a good day.